It will strike 10:02 any second, so I will actually start. Welcome to our last webinar for this season. Next webinar will be in late August. But today you are going to listen to the art of metallography, color etching, and number 13 of our webinar series, which we are maybe 1/3 into the series now, which address both metal and polymer webinars for the metal and polymer industry. And here you see, if you have really good eyes or glasses, better than mine probably, you see the registrant list of today. So there are a lot of registrants, and we are expecting more to join while we are starting up. And you will, since you will get the PowerPoint afterwards, you can take a closer look and zoom in on the picture. And the webinars, our WebLearn series, are addressing the metal and polymer industry. And it is supported by the Knowledge Foundation in Sweden to help us to provide effective competence development for the industry. And if you found your way here, you will also be able to find the way to all our coming webinars in the future. And the moderators of today, the gray person to the left that has not been color etched so far is me talking, that is Stefan. And later on, you will meet my more colorful colleague, Madeleine. But the main actors of today, or the artists maybe, considering the subject, is our colleagues from here at the School of Engineering, Professor Attila, and we also have Björn Romei and Vasilios Forlakidis. In presenting in that order, it will be really interesting to listen in on the subject today. Would you mind jumping to the next one?
Yep.
And the format, as you see, the presentations will start any minute now, and then after around 50 minutes, we will move over to a panel discussion with our presenters, and also where you will be able to participate, of course, which we urge you to. And then we will wrap up within 1.5 hours. But if you still have more questions when we wrap up, do stay online, and as our presenters will stay as well for a short while, where you can connect and ask some more questions if you want to. And the class structure of today, or the rules of the classroom. If you are not the one talking, please keep your microphone turned off. And of course, we welcome questions during the presentations, but do write them in the chat, and we will address those at the end or during the panel discussion. And do take part of the discussion towards the end, where you can share your experience and ideas. And if you don't want to be seen during the panel discussions where you might have the opportunity to talk, keep your camera turned off as we are recording this webinar. Yeah, the last thing, breakout rooms was not valid for today. And if you are unfamiliar with Zoom, down below on the bar far to the left, you have the on and off for the microphone and also the camera. And some way or to the right, you have the chat function, which opens the chat box where you also write your questions then. And probably some answers you can write there later on when the panelists ask those questions. And by that, I hand over to our first presenter, Attila Diosegi, on the topic of today, color etching. The floor is yours, Attila.
Thank you, and welcome everyone to this webinar. We are going to go to an interesting topic, related to cast iron, color etching. Color etching have been a very important method during the last 20-25 years, introduced in the cast iron investigation, in cast iron research, even in companies. And we are going to give some backgrounds about the role of the color etching, about the theory of color etching, about practical issues, and in the end we are also giving you some examples, and finally we will be able to discuss with you. So the first slide you can see here is a phase diagram of iron, carbon, silicon, cast iron, and you have cast iron with a carbon content over 2%, and below that is steel. And what you can see is that approximately for 20-25 years ago, the availability to investigate cast iron morphology was a little bit delimited. There was a couple of different methods to be used to understand the morphology and the background of cast iron. To the right, you can see the polished cast iron samples in light microscope, lamellar graphite iron, and at the same time we have also some deep etch, some observations. We could understand the shape of the lamellas as well for the compacted graphite iron, and the shape of the compacted graphite, and the nodular graphite and the shape of the nodular graphite. To go more deeper to understand the metallic matrix, then we have mainly two methods to prepare the samples. The one was the pickrel, the other the nickel etching methods. And as you can see in these pictures, it was possible to see beside the graphite particles the metallic matrix. In this picture, you could see pearlite grains and pearlite lamellas. In the case you wanted to understand the graphite morphology, then the eutectic cells, then it was aqueous ammonium persulfate solution used for etching and promoting the phosphide eutectic, and that was the way to count the number of eutectic cells. So this was our knowledge about 20-25 years ago, and fortunately after 25 years we have a completely different understanding on the morphology of cast iron. We can make only a single preparation, not in 4 steps like for previously, to understand the different components of the morphology. Now we are seeing simple preparation step by doing color etching. Then we can see the different behaviors, the eutectic cells, the dendritic network. We can see the pearlite lamellas in the same picture. Furthermore, we could thanks to the color etching, being able to understand the dendritic network. We could understand the pearlite grains, how they are placed and developed in cast iron. So in this presentation, we are going to discuss the background. So I hand over to my colleague Björn Domey to start his presentation.
So I will focus on how the color etching works, and also a bit about how you can interpret these colorful patterns that emerge when you do the etching. And there are more than one ways to color etch, but the one we feel is most important is, and that we have most experience with, is based on an etchant developed by a gentleman called Motz. He emphasized that microsegregation is often an overlooked aspect of ductile irons. And he noted that chemical composition of both ferrite and pearlite actually varies considerably at the microscopic scale. Since silicon is often the most important element in cast irons, he designed a color etching method which was specialized in revealing the microsegregation patterns of silicon in ductile iron. And the original composition was that it has 10 grams of potassium hydroxide, 40 grams of kalium hydroxide, and 10 grams of picric acid, and then diluted with 50 milliliters of distilled water. The mechanism is that this etchant oxidizes the surface of the metallographic sample, forming a film. And the film grows at a rate that is dependent on the underlying silicon concentration. So that after a while of etching with this etchant, the film is thicker in the parts that contain more silicon. Then light interacts with the film through thin film interference, which causes the film of different thickness to have different colors, or the light that is reflected has different colors, which then reflects the underlying silicon concentration. And thin film interference works in that the light is both reflected at the outer exterior surface of the film, but also on the inner surface of the film. And then the two reflected light then interact when they leave the surface. And the interference can both, interference can both be constructive, where the intensity is increased, or it can be destructive, where the intensity is decreased. And it depends on the relation between the length of the light wave, or the wavelength, and the thickness of the film. So the relation between these two lengths then determine whether the interference is constructive or destructive. So depending on the film's thickness, certain wavelengths or colors are reduced and certain other colors are emphasized. And this then causes a light spectrum which depends on the film's thickness. And this is what you actually see when after you have done the color etching. Similar effects can be seen in, you might be familiar with, for example, when a droplet of oil ends up on a wet surface, or maybe on a soap bubble. Or you can even see it in the oxide films around a weld, for example. So when Jürgen Motz introduced this method, he also verified that the troughs and peaks of silicon concentration correlated with the observed color patterns. However, these height maps that he showed to demonstrate the correlation were not so easy to compare to the color patterns. So in later work, we have tried to compare more carefully and verify that it correlates well with silicon. So on the left here, you have a color etched surface of compacted graphite iron. So the blue regions here correspond to the regions which are rich in silicon, and the yellow regions are have lower concentrations of silicon. And we measure the same region with EPMA to map the concentration of silicon in this region. And on the right, you see the map of the silicon concentration. And here we have used a color scale on the concentrations which imitates the effect of the color etching in order to make a more close visual comparison. And you can see that it correlates very well with the patterns you see in the after color etching. Another thing to note is that these patterns that you see, what they represent. So you can actually see some strange features. So you have blue around the nodules, and you have blue in the eutectic cells, and you have some blue in some kind of branch-like structures. And if we look at the material when we have treated it in a different way, on the right here or in the center, here we have quenched the material from when it was only partially solid, and the liquid regions solidified as fine lead-barite, which you can see as this blue or darker regions. And here you see that the branched structures, which we call dendrites, they exist here, and they can actually be seen in with the color in the color etching too, because of their richness of silicon compared to the background. And you can also see that we have this eutectic cells of compacted graphite, and that we have shells of austenite around the spherical graphite, which you also can see as blue auras around the spherical graphite with the color etching. So what you will see with the color etching depends on how the material has solidified, and it reflects in some sense the solidification structure, the early solidification structure of the material. So hypoeutectic cast irons, where you have a relatively low carbon content or carbon equivalent, tend to solidify in a way where this dendritic structure begins solidification. And after a while, eutectic cells or graphite start growing in the room between the dendrite arms. While when you have a near eutectic cast iron, then the eutectic cells and these branched dendritic structures tend to grow or start to grow pretty much at the same moment, and they grow more in parallel. This means that they will have a similar concentration of silicon, as we will see later. And if you have a hypereutectic cast iron, then you can have primary graphite, but below a certain temperature, it will grow. The rest of the structure will grow quite similar to the near eutectic. On the left here, we see another map where we have measured concentration of silicon of a compacted graphite iron. And here we also can compare to the microsegregation of manganese on the right. Just to illustrate that the silicon segregation patterns often correlate quite well with the segregation of other elements, such as manganese. Here it segregates inversely manganese. So manganese is found manganese is found rich in the areas where silicon is impoverished, and it's found in low concentrations where the silicon concentration is rich. And here we look at in the same way on a ductile iron where we have a spheroidal graphite. And you can see that this is true also here. In this graph, we have rearranged the concentration data of these two materials, the ductile iron and the compact graphite iron. And we have ordered the concentrations from the earliest solidified parts of the material to the last solidified parts of the material. And you see that when we do this and compare the two materials, it seems like silicon, copper, and manganese segregate in very much the same way in both ductile iron and compact graphite iron in this case. This might not always be true, it might depend on the solidification time, but at least in this case, for a solidification time about 10 minutes, there was not big difference between CGI and SGI. Another thing you can note in these profiles is that silicon continuously decreases as the volume fraction solid increases. So the more silicon decreases, the more the material solidifies. And this means that we can, since after the color etching, the silicon concentration is reflected by a color. It means that a certain color will correspond to a certain moment in solidification when this austenite crystallized. And this makes it possible to use the color etching to understand what parts of the metal matrix has solidified before other parts by looking at this color scale and comparing. And as we said earlier also, which maybe is emphasized in this graph, is that the silicon concentration also correlates quite well with segregation of other elements. There are, however, some factors which make the segregation patterns, which you see with the color etching, a bit more difficult to interpret under certain conditions. So for example, the segregation behavior of silicon depends on, for example, on the carbon content and the silicon content. So under certain combinations of carbon and silicon content, you can get quite strange patterns. So in the graphs below here is from a study where they have showed that the segregation behavior or the segregation of silicon and copper, for example, increases as the carbon content increases. It's a bit difficult unit on the horizontal axis here. It's atomic %, but you can see that they have marked where they have the eutectic composition. So when we have an increasingly hypoeutectic material, we can note that silicon segregates quite differently. This or here on the left, you see a color-etched micrograph where this is emphasized. This is a material where we have a quite low carbon equivalent and at the same time high silicon content. And in this case, we actually saw that instead of the core of the dendrites being rich in silicon, they are actually impoverished in silicon, have a lower concentration. And then the outer parts of the dendrites, which formed later in the solidification sequence, actually have higher concentration of silicon. We made a calculation using data from a thermocalc database in order to estimate what the expected segregation would be. And then we actually see on these curves for this alloy that the concentration of silicon in the metal matrix actually increases until about 60% of the material is solid, and then it starts to decrease again. And in these special cases, it might be a bit more difficult to interpret the structure, because a single color can refer to different parts of solidification sequence. Another factor that can make it a bit more difficult to interpret the structure, at least in terms of solidification sequence, is that ferrite tends to etch at a different rate or a slower rate than the pearlite, which means that it becomes the pearlite becomes blue earlier than the ferrite does. This is of course good if you want to see the ferrite, but it can mean that this correlation between the silicon concentration and the color is not as simple in this case. The rate of coloring also depends on the ferrite orientation. So you can kind of see that some of these ferrite grains are a bit more blue and some are a bit more yellow. So if you want to see the solidification structure, the color etching method works best on fully pearlitic or fully ferritic materials. One more aspect that can be important to understand is, so earlier I showed that in high or hypoeutectic cast irons, the dendrites form at an earlier stage before the eutectic. And this actually makes it can make it easier to distinguish between the dendrites and the eutectic. In the picture on the left here, actually I got this from Vasilios, which will also present here after me. Here you see that even if we have these dark eutectic cells, we can often see the blue dendrites through the eutectic cells because of their higher silicon content. On the left, on the right, on the other hand, where we have a hypereutectic ductile iron, you can see that the shells around the nodules actually have very similar color as the dendrites, which makes it very difficult to differentiate the two because they have similar silicon concentration. So in summary, Motz reagent oxidizes the metal matrix of cast irons at a rate which depends on the underlying concentration. Light then interferes with this film, giving rise to colors depending on the thickness of the film, which reflects then the underlying silicon concentration of the metal matrix. In typical cast irons, silicon tend to decrease monotonously as the volume fraction of solid grows, meaning it is possible to draw a direct connection between these two. However, under certain conditions or certain factors can make the color patterns a bit more challenging to interpret. At very low carbon equivalents or carbon contents, it can be difficult to differentiate early and late crystallized parts of the austenite because the color can both be yellow early and late in solidification. Moreover, the metal matrix containing a mix of ferrite and pearlite can be challenging to interpret as they etch at different rates. And in near eutectic cast irons, dendrites may have similar color as the eutectic cells, which makes it difficult to distinguish the two. So now I have talked about how it works, and now Vasilios will talk about how to actually perform this this etching.
Yes. Hello, everyone. I'm going to present how we can perform the color etching in practice.
Sorry, Vasilios, I'm trying to give you remote control here, but I'm not sure I am.
That's all right.
I'm doing something strange, or it's not responding.
No problem. Okay.
Yeah, now.
Good. Thank you.
I gave up mine now manually,
Oh,
so
that
maybe we have
that
to
was
do
the
that.
problem. Thank you, Björn. Okay, so now, Vasilis, the floor is yours.
Okay, thank you. Good. Yes, I will show you how to perform the color etching. There are two different formulas for the preparation of the Motz reagent. In the first formula, we are using 10 grams picric acid, 10 grams sodium hydroxide, 40 grams potassium hydroxide, and 50 milliliters distilled water. And the picric acid is in form of powder that is immersed, moistened with water. And this is flammable and also toxic. For this reason, there is also a second formula, formula B, which we are using instead 50 milliliters of picric acid solution, 10 grams of sodium hydroxide like before, and 40 grams of potassium hydroxide. And the difference between these two formulas is that the formula A can be used several times, while formula B lose its potential after a couple of times when you are using it. The safety data, we consider that the Motz reagent carries the hazard properties of the picric acid. So we treat this reagent as explosive when it's dry and toxic when it's in contact with skin or if inhaled. Here is the color etching equipment setup. On the left, we can see that for the preparation of the color etching treatment, we need a glass container on a magnetic stirrer with heating. At the bottom of the glass container, we have a stirring magnet rod. Here you can see also a sample holder with a magnet, the sample at the bottom. And there is also a temperature probe that controls the temperature of the mixture and can adjust automatically the temperature. Here on the right, we have the setup as it is in operational form when it's operated. Here are the process parameters for the etching. The reagent must hold in temperature between 95 degrees Celsius and 100 degrees Celsius. And as the lower is the temperature, the slower is the reaction. The stirring speed has to range between 0 and 150 RP rotation per minute. And this depends from the thin layer of the surface of the reagent. I'm going to say a few more things about this later. And the etching time is ranged between 2 to 8 minutes. And the etching time is dependent of the silicon content, of the coarseness of the macrostructure. The coarser is the macrostructure, the slower is the reaction. The temperature of the reagent, the composition of the reagent. During the process, we have evaporation of the water. So the composition of the reagent is changing, and that's influence also the etching time. and also the freshness of the sample surface. If the surface of the sample is polished and then immediately do the color etching, then the time that is needed for the color etching is smaller. We need less time. After the etching, we can clean the sample by using running water, and of course we control the microstructure by using an optical microscope. There are a few problems that can occur when we are doing the color etching technique. The first is that after the etching, we get the under etch microstructure. As we can see here in this micrograph, you can see that the achieved color, the spectrum, the color rate is smaller than the targeted color rate in order to reveal all the different microstructure features. So a solution to this is to immerse the under etch sample and wait a little bit more, and also to increase the etching time for the next one. Another problem, the second problem that we can face during the etching is the opposite from the previous. It's when we have an over etch microstructure. Here in this image, we can see an over etch microstructure, and we can see the achieved color range. It's much larger than the appropriate color range, meaning that less etching time is needed. And the solution to this, unfortunately, when this happened, we must regrind and repolish the sample, which is time consuming, and also to reduce the etching time in order to get the proper color range. Here we can see an example of the ductile iron microstructure of the over-etched sample on the left and the normal color etched sample on the right. As you can see, the appropriate color etched sample, the sample that has been etched has a well-etched structure. You can see that the different microstructural features are much more distinguished. You can see very clearly where is the austenite together with the graphite particles. We can see some dendrite arms alone, and we can observe also the dendritic phase very clearly. The last problem that can be occur during the etching process is that thin film form at the surface of the solution during the etching. And if this film it's in contact with the etched surface, then it's hinder the etching process. So it's something that we have to get rid of this. It's an unwanted impurities. So in order to get rid of this, we have to steer the reagent with higher speed. It's one of the solution. And also we can also reduce the etching temperature. And this was my last slide, what I wanted to say. And now I hand over the presentation to Attila, that will continue with some real example of the etching technique. Thank you very much.
Thank you, Vasilis. So can you please hand over the remote
Yes.
to me, Vasilis?
How we do this?
Good question. Here we have, let me see if I can.
Okay.
Okay, Attila, I think I will change the slides and you can just say next if we cannot fix this. Okay, Attila, let's try it this way. I will handle the slides.
Okay. Good. Then thank you for Björn and Vasilios for the presentation, and we have found a lot of applications for color etching, and it was really helpful to interpret the material, the solidification, the property formation in cast iron, and also we could also collect some information related to casting defects, which can be of interest for foundries. So please go forward. So I'm going to present a couple of slides here. This is a color etched lamellar cast iron, a lamellar graphite iron, and it's very interesting to see that in the same picture you can see both the primary dendritic phase, the eutectic cells interfering the graphite, and with a little bit higher magnification you can see also the pearlite lamellas. So practically you can see everything in the same sample prepared, excepting the austenite grains, which is another matter of technology to prepare. Next, please.
And just say, Attila, now
Next.
you have remote control. as
Okay,
well.
thank you. I have the.
I managed
then,
to fix it.
then you are, and I have also the. You can see my laser also, isn't it?
Yes.
Good. Then in the similar way, we can see the compacted graphite iron, slight hypoeutectic one with dendritic network interfering with the eutectic cells. We can see the graphite and the pearlite lamellas inside. Next picture is a color etched compacted graphite iron in transition to nodular cast iron, and even in this case you can very well distinguish between the graphite of compacted shape in an eutectic formula and then the transition to the nodular cast iron. So you can see the graphite, the pearlite lamellas are also well distinguishable in both the shell around the the nodules, and also in the last solidifying area, it's very clear how the perlite is looking out. Then for those who are fighting with production of cast iron, then color etching could be also of a useful tool. In this picture, I'm showing a color etch subsurface porosity in a green sand of cast iron part. The porosity is collapsed, and there is a interface between the different parts of the cast iron, and it's interesting to see that this lower part have a much finer dendritic network compared to the one over the separating line, which indicates that the solidification of the lower part has happened much earlier, much effectively, and the one behind the line, it's solidifying slower due to this coarseness of the dendritic network. More defects you can see. This is a color etched subsurface porosity in green sand and cast nodular iron, and this surface is the mold surface, and the bubble have been formed over just gas have entered into the liquid metal and could not pass through the bark material to leave to the surface. So you can see very clear how the bubble structure looks out in a higher magnification. You can see very well a rim of ferritic structure, and this is indicating that this surface was solidifying in contact with the gaseous material, which have a relatively low heat extraction capacity, making that the solidification of this surface was very slow. Other examples are subsurface slag porosity in green sand casting. In this case, it's interesting, or it can be seen that a bubble or a gas porosity is formed, and why we know that this is a slag initiated porosities, because we have a tile in connection to the porosity, and the surface of the casting is along this upper surface. Let's go forward. Yes, and this is a higher magnification of the same picture, and here you can see that. I'm sorry. Yes, now I'm back here. So here we can see this tile formed, and also the surface is completely different in the solidification. It's not anymore that rim of gaseous element, which delimited the solidification time as in the previous case. So color etching was very, very useful to understand how the austenite network form, or how the austenite network looks out in a cast iron. And for this reason, we performed a sequential investigation by using a part of a sample and preparing by preparation and etching and taking picture, and then after taking picture we reiterate the same process by polishing again, taking away approximately a couple of micrometers of the surface and re-polish, re-etched, and new picture. And in that way we could go through the structure of a in this case laminar cast iron, hypoeutectic laminar cast iron. An example of a color etched picture, you can see how the dendritic phase is distributed, and then using image analyzing and differentiating the dendritic network from the rest of the phases based on the color differences, we could obtain a picture on how the dendritic network looks out in a certain layer. And then by reconstructing the obtained layers, then we could obtain a three-dimensional model of the dendritic network, which is very useful when it comes to trying to understand how the dendritic network or that part of the metallic phase influence the tensile properties or the thermal properties of casting. We are not talking about these foundings now, but these are the background of how to understand the distribution and the morphology of the primary dendritic network. More defects you are facing with in foundries, it's the shrinkage porosity, and shrinkage porosity can be found in polished sample on the cutted surface, and from that information it's quite difficult to understand how this defects are formed, but by color etching and looking to the picture to the right, you can see that the dendritic or the porosities in between the dendrites, the shrinkage porosities are in the last solidifying area. There are eutectic cells, complete eutectic cells around or in between these dendrites, between these porosities. So from this, using color etching, we could distinguish that and understand that this type of shrinkage porosity forms in the last solidifying area in between the dendrites. Penetration is another phenomenon found in foundries producing cast iron, especially for laminar cast iron, and taking out samples from different parts of the penetrated area and color etching them, we can find completely different morphologies. In the upper one, you can observe that the particle squeezed in between the sand particles, metal droplets, they form and include both primary phase, here in the middle, the bluish phase, and the eutectic phase around with the graphite particles, graphite lamellas. So this indicates that the metal was pressed into between the sand grains at an early stage of the solidification, while in the droplet below, we can see there is no primary phase. It's only eutectic composition. It's only eutectic structure with lamellas and eutectic cells, which indicates that this is a material squeezed in between the sand when the composition of the metal reached eutectic composition. In the next picture, I will try to explain how this can happen. We have once again a iron, carbon, silicon phase diagram to the left, and we have a density diagram which indicates how the density of cast iron increase by temperature decrease until the liquidus temperature, when the primary phase is precipitated, where a much sharper density decrease or less sharper density decrease continue until graphite precipitate, which is a light phase, and the precipitation makes that the density of the cast iron is decreasing. So the material found in an upper color etched picture indicates that this material was squeezed in the early part of the process, where the liquid was over the solidification temperature, the liquidus temperature, while the lower one, where we have only graphite phases and no primary phase, indicate that this was squeezed from between the from that part of the solidification when only eutectic phase existed. There are many different interesting pictures we have in our directory, but unfortunately I cannot show more due to the time. But as a conclusion, I can mention that color etching is the most significant method applied during the last 25 years to improve the understanding related to the solidification process and defect formation mechanism in cast iron. Color etching replaced the separate previous etching methods based on pickerel, nickel, persulfate with single preparation route using picric acid. So we save also time and improve the dimension of understanding visually in the same picture, the faces. And thanks to color etching, we understand better the solidification chronology of cast iron. We understand better the precipitation and the role of primary austenite in cast iron. And we also understand better the source of casting defect formation in cast iron. So with that, I leave the word over to Madeleine.
Thank you, Attila. I will put my camera on as well, if I can manage that. Yes. Okay, thank you very much, Attila, Björn, and Vasilis. Very fine presentations. And now it's time to start a discussion. And we, of course, this is in the WebLearn webinars. We, of course, would like to interact with you and get your experience of this area. And you get the possibility to discuss your experience with the experts. So we will start with the question now. Are you using the color etching method in your profession or in your work? And what is your experience? And we will try today that you please share that in your chat. So 1 minute to everyone. Find the chat and write something short, and then our presenters will start the discussion with you. Later on, you can of course also raise hands if you want to express yourself that way with words, of course. So please start the chat. And I think Attila, Björn, and Vasilis, I will stop sharing the presentation.
Yes.
So, and anyone who wants to be on camera, you can put your camera on. So maybe we will get more contact. So we will keep track of the chat. Okay, while we are waiting for comments, we will try the first one from Angela. Thank you very much. Thanks, very interesting. This type of reagent is included in ASTM E407 ?
I can say that I don't know if it is included there.
This
if anyone
reagent,
knows, please speak up.
No, I don't think it's included because it's so young, only 20, 25 years old. 88 was actually when Jürgen Motz presented his paper, and since that it was around in the middle of 1995 when the first attempts was made, and it was in the second part 97, 98 when the first papers appear in the literature using color etching as a etching method. So I don't think it's included in any standard, any description according to our knowledge. No.
Good. So next, hello from Robert. I'm not using color etching, but do we have possibilities of using it in analysis AI 7075 ?
So on an aluminum alloy, I have not tried this, but so I don't know what the result is. But it contains silicon, so maybe it will work. So you're free to try. I don't know what the result will be, unfortunately. I also saw there were a Swedish question also before that I would like to address before we lose it. So Jonas Jadestig was asking, so is this type of etching, does it form a kind of layer on top that is easily removed, or is it more permanent color patterns, more similar to Nittal? And it's kind of a mix of that. I mean, we do form, the principle is that you form this oxide film on top of the surface, and the thickness determines which color you see when you in the light that is reflected. But this film is actually quite robust. You can rub the surface with cotton quite hard without removing or damaging this layer. So you need to kind of actually forcefully grind or polish the surface in order to remove the layer or damage the layer.
Okay.
Hope that answered the question.
Yeah, good. We have also a question from Max, a student in the Founder Master program, I think. Hello, Max. Thank you for an interesting presentation. Have you ever tried etching on an ferritic cast iron with Motz reagent? And if so, is the result usable?
I have tried this, and it's more difficult to see this early solidification structure. The dendrites and the eutectic cells, you can see them, but it's not as clear. But you do see this acicular ferrite, and it etches at a different rate than the retained austenite. So it depends on what you want to see, but it has an effect there too. Yes.
Okay, and we have a question also from Göran. Thanks for a very interesting presentation. It looked like the sample was upside down during the etching operation. Is that important, and why?
Yes, maybe I can answer this. No, it's not important. I have used both methods. I have used both upside down and close to the surface, the sample surface, and in both cases it works. So they can use another type of holder while the etched sample is has a face to the reagent surface and still works.
Okay, great. We have one more question from Anil. Firstly, thanks very much for everything. Very important information was included. I work about steels, general, and cast iron interests me. This webinar has been very productive for me. If it's reorganized, I will be happy to participate. Finally, my question for Dr. Vasilis. Can we use both formulas for each cast iron, formula A or formula B? There is a chemical difference between, yes, what kind of harm or benefit does it have for cast iron?
Yes, you can use both formulas for all kinds of irons, for sure. The thing is, if you use the formula B with the solution, it's more safe somehow. You don't have to deal with the powder, that it's very flammable. So it's easier to be handled. On the other hand, you are losing from, let's say, the robustness, how much you can use, how many times you can use the solution, the reagent. You can use less time. But yes, it's for all. Both formulas are working very well. It's in reality the same reagent. And if there is any chemical differences between, I think the same chemical composition. There is no different chemical. I'm not sure about the composition, but at least all the elements are the same.
So from what I understood, it's that the main difference, I think you explained this, Vasilis, that in one of the formulas you use kind of powder form picric acid, and in the other one you use dissolved picric acid. And that seems to be the main difference, but I think they try to keep the chemical formula, I mean, in terms of the amount of picric acid versus and the concentration, pretty constant. But I haven't checked, but I think that's the idea.
May I have a question also myself?
Yes.
It's about the description of the method, and Vasilis, did you talk about the temperature influence on the results? That this etchant has with that composition, original composition, we have boiling temperature on around 120 degrees Celsius. And you mentioned that you are doing the etching in a temperature range somewhere. What was that?
95 and 110.
Yes, 95 and 110. And what is the difference if you have a 110 to 95?
It's a big difference.
Yes, and what is that? Is that so that when you have a high temperature, then you have a faster
Yes.
process, and it's okay for impatient people, but it's very easy to run over for over etched situation when you use too high. So I think it's worth to keep the lower temperature to have time to look to the results and go back and continue to etching, rather having a lower under etched than an over etched situation.
Yeah, exactly.
And then I think there are other aspects also that maybe we haven't taken up, but I remember that on the other side, you could also preheat your sample, and by preheating the sample, then you can extend the time of etching, or making a little bit more controllable the process. For example, in an oven, you can preheat your sample to a certain temperature just to have a control over that where you are, and that means that the temperature between the interface of the metal and the liquid, the etchant, the temperature differences are promoting the grow velocity of the oxide. So as smaller difference you have, as slower will be the grow rate, and it will be less demines with fast over etching.
Yes.
Any other questions? I have seen a lot of known people from practicing in foundries. Can they come in and have some questions, or I can see a very experienced person here, Andre Ramos from Tupi in Brazil. Andre, could you connect to this discussion and say something about your experience in using color etching? Andre, are you there?
Yes, hello. Can I use
Hello.
my microphone?
Yes, we can hear you.
I know in Brazil it's quite early.
Yeah, it's
now
6 a.m.
6. I think that is remarkable that someone goes up early in the morning to participate in a color etching seminar. So you are a top person. Thank you very much.
No, thank you. It was a very good webinar. I was thinking during the webinar that I'm currently using it to investigate shrinkage porosity formation case in our foundry. And I was looking through some color etching samples yesterday in Tupi. It's really good to see your presentation, because it gave some more ideas on how both in the operational part, how to instruct our technicians, because sometimes they go through and over etch it, and sometimes it's under etched when I see the samples. So it reminded me of some points that I can discuss with them to get better color etchings. And also we are experiencing with different levels of carbon and silicon and seeing the results of those in color etching. So Björn comments about how the level of carbon can influence in the segregation profile of silicon was very interesting, and maybe I can use this information to test some more. So thank you very much for your presentation. It's always good to see you.
Thank you for your comments. Do we have more people who want to comment?
I have one thing from the chat from Angela. I'm from Colombia. In this momento, it's 4:16 a.m. Thanks for the information. What is the procedure to continue participating in these conferences? Well, if this is the first time, I can tell you that after this webinar, you will get the recorded webinar and so on, and also information on how to register for the coming webinars. We will continue this autumn to have more webinars. We have had 13 this spring, and we will have more this autumn. And you can also, if you have topics that you're interested in, so please, you can suggest topics as well, because we want these webinars to be really up to date and what you need, so to speak, out there. So I hope that answers your question. Thank you.
I could add some more comments to your Madeleine, and is that this is lattice and polymers, and they are different groups of
Now your sound disappeared, Attila.
topics, and cast iron. And I think this was the 4th seminar in this area. We have other topics, light alloys, we have polymers, we have surface technology, we have I think 5 different you find on our website. And for those who are interested in cast iron, and I can say that we have one webinar related to molding material, one related to melting procedure of cast iron. We had one related to penetration defect formation and production of cast iron. And now this is the 4th with color etching. And those who have not been able or have not information about the previous one, just contact me and I can share with you and give some material back to those webinars who have been passed. And we plan a couple of more webinars during the autumns, even in the area of metallic materials or iron-based alloys and cast iron too. And yes.
Great. So guys, you had a question also to the audience. What use do you see in your profession or in your company if you're not using this method right now? What do you see for challenges and opportunities? It would be great if you write something in the chat if you have comments on that. So Attila, Björn, Vasilis, if someone is not using this, what would be the main reason to start using this method?
I mean, in general, you see, I mean, you don't get a very clear picture of the solidification structure besides the graphite unless you use this method. You see the graphite structure most clearly, and if some help of some other etching method, you can see the pearlite and ferrite. But since many of casting defects, they actually form during solidification, so then it can be really useful to also see the early solidification structure and how the pores are formed in relation to this. And also, I mean, the later eutectic and the solid state transformation, they are affected by the early solidification structure, even if you don't see it always clearly, because of these segregation patterns and such. And the eutectic can only grow in the space between the dendrites, which also kind of delimits its distribution.
Good. We have some input here from the chat. Dharmateya says, I worked with this technique in my master thesis, Dr. Dumay as my supervisor. I had observed that the volume of the etched sample and the surface in contact with the reagent were also influential to the film concentration, along with the many other factors that were discussed here today.
Yes, this is an one more kind of a complication with this etching process, that the sample itself has a temperature when you submerge it, and the temperature at the surface where the reaction occurs is then kind of it takes time for the surface to heat up if you have a large sample. So then it can, where the surface heats up more quickly, you can get the reaction going quicker, and then you have further into the sample, a large sample, you can have a bit, it takes more time for the reaction to pick up. So then you can have, I mean, it doesn't color as evenly as you want. It's a bit, the reaction is a bit ahead of time in near the edges, and then a bit delayed in the center. From my experience, one way to tackle this is to use a bit lower temperature and etch more slowly, because then it has more time to heat up, and the result is more uniform. There have been attempts also, I know, to preheat the sample so that they are near the temperature of the solution you submerge in, and then you can remove this effect this way. But I've been a bit suspicious that you kind of that you damage the surface or oxidize the surface beforehand if you do this heating before you submerge it, so the surface quality is not as good. But I don't have personal experience with it.
Okay, thank you. And we have a question here from Anil. We've seen some color spectrometers. They were very similar to each other. How do we distinguish between them? For example, blue and its shades were very similar to each other.
So when you do this etching, the goal is to stay within the first period of colors, so that if you over etch, then you will have several periods having similar colors at different silicon concentrations. So basically, if you find that you have kind of recurring colors at different radius of the dendrites, or at different distances from the center of eutectic cells, then it tends to be over etched. So this relation between the color and the silicon concentration is, it depends on that you have successfully stayed within the first period of this color pattern. Or yeah. So the in general, the principle, when you have finished etching, then the part of the surface which have the highest silicon concentration should be bright blue. That's kind of the goal. And then the rest of the colors, or the rest of the lower silicon concentrations, will then have more towards purple and red and yellow.
Okay.
And once last comment to the question, what is or why to use color etching? I think that it's beautiful colors, and those who like variation of colors and beautiful pictures of geometries and just print up a picture and put on the wall could be nice using color etching as an art.
I'm actually guilty of having a color etched picture as painting on my wall.
Yeah, so that's a tip for everyone. Okay, we're starting to get closer to 11:30. So Attila, you promised that anyone who is even more interested and want to ask you even more questions, you can stay after 11:30. So we will stay, but I think maybe we will formally start closing this webinar. Would you like to say some, except that the pictures looks very nice? Do you want to add something more to conclude this, Attila?
I would like to encourage you to use color etching in spite of our difficulties, in spite of our efforts you need to do, because we can we have seen or we have a enormous benefit of using color etching in understanding cast iron, in understanding properties, in understanding defect formation, in understanding the solidification process. So I think it will be important that this method is used by many other persons to develop this area of and to develop generally the cast iron understanding and properties and process to produce cast iron. So and now we know us, you see our contact information, so we are happily in answering any question you have related to color etching, and please feel free to contact us. So do you think that you need some kind of cooperation in that field? We can also offer you and help you. Just contact us. So from that point of view, I would like to thank you very much for your attention, and thank you very much to Björn and Vasilios for their presentation, and also Madde and Stefan for their management of the webinar.
Thank you very much, Attila. Just some small things. As I said before, you will get the recorded video of this webinar, and we always collect and document the webinar in a so-called Padlet. It's like a bulletin board where you also can continue writing and network. And if possible, please fill out the evaluation form, very short, 2 minutes. So this is the last webinar for this spring. So we will come back again in the autumn. And the topic of the next webinar, the 26th of August, is casting process simulations, applications, and development. So, and you will get all information how to register on that webinar in your mailbox. So thank you very much. We will say goodbye. But as Attila promised, if you are really curious and want to discuss more, please stay on.
Mhm.
So thank you very much. Thank you so much for your contribution in the chat.
Good. I have a cup of coffee with me, so and some.
Yeah, you have to have it. You have to hold it.
And some mineral water from. So I can talk limited.
Yes, and I will stop the recording as